conservation of energy and linear momentum. Alright, to describe this principle, we have an example here of a car with a mass of 600 kilograms and a velocity of 15 meters per second smashing into a car with a mass of 1500 kilograms and a velocity of 5 meters per second in the same direction. So, part A. What is the final velocity of the cars if they stick together? That's an important thing to note, if they stick together. And B. How much kinetic energy was lost during the collision? So one of the important things to note about conservation of energy is always conserved. However, when you have a collision, your kinetic energy may not always be conserved. It may turn into heat, it may turn into deformation, sound, light, other things. Your energy changes form, it just doesn't stay necessarily as kinetic energy. For momentum, linear momentum is always conserved. And so for that problem, we have to do this in two steps. We have to use linear momentum, and then we have to use conservation of energy. So for this, we have our known values. We have our initial mass, and we're going to go ahead and call the more massive car A, and the less massive car B. So go ahead and write down the knowns. MA equals 1500 kilograms, VA equals 5 meters per second, MB equals 600, and VB equals 15 meters per second. And then something else to note is from part A, it says if they stick together. So what that means is the two cars after the collision, they are stuck together. What this means is that these two cars have the same velocity. And when they have the same velocity, that simplifies down our number of unknowns and makes this problem solvable. So, and our unknowns are going to be our final velocity and our kinetic energy lost per questions A and B. So the first thing we need to apply is conservation of linear momentum. And the way we start out doing that is by drawing a moment diagram. So that's always the best way to start physics problems, is to draw yourself a picture. So, and basically what we're going to do is we're going to say after the collision minus before the collision equals during. So this is kind of going to be an equation, and by kind of, I mean it's actually going to be an equation. So after, go ahead and draw yourself a picture. You have two cars. You have A and you have B. These two cars are stuck together and they have final velocity v sub f. Before, you have car B slamming into car A. So, and they both have different velocities, VB and VA. And then during the collision, there's some interaction happening. There's crumpling, there's sound, and that's what's happening. So it's just like the time that the car is kind of collapsing together, or the two cars are collapsing together. So for this, we can go ahead and write out some sections of the equation that we have. So for after the impact, we can write out the standard momentum, like piece of momentum, and what that is just mass times velocity. So for after, we have two masses, so MA plus MB times their velocity, which is v sub f, minus before. Before is going to be m sub b VB plus m sub a VA is equal to Deering. And technically during the Deering section we have forces being exchanged, and basically we have impulse is what's happening. But we're not going to worry about that section. We're just going to say that the collision happens really, really, really fast, and thusly that section can be reduced to 0. So for the Deering section, for pretty much all of physics, you can say this is going to be 0 unless you're dealing with impulse. So we can go ahead and combine some stuff and reduce it. So we have an equation here with MA plus MB minus MBVB plus MAVA equals 0. Oh, and then there's a V sub f out here. Very important, V sub f. So that's what we're solving for. So then go ahead and solve these equations for V sub f. And when you do that, you will end up with V sub f is equal to MBVB plus MAVA all divided by MB plus MA. When you plug in all of your numbers and solve, V sub f is going to be equal to 7.86 meters per second, which is always good. That your V sub f value is between your VA, which was 5 meters per second, and your VB, which was 15 meters per second. If it happens to be larger than your largest velocity or smaller than your smallest velocity, then there might be a problem. But in this case, we've done it right. So it comes out as 7.86 meters per second. Alright. So moving on, conservation of energy. We need to find out just how much energy was lost inside of this collision due to heat, deformation, and other factors. So for kinetic energy, that's always equal to 1/2 times mass times velocity squared. And then to find out the amount of kinetic energy we lost, that's quite simple. We take, we just say the kinetic energy lost is equal to how much energy it had initially, so KE initial, minus how much kinetic energy it has at the end, so KE final. We can go ahead and write that out into an equation as KE lost is equal to 1/2 times the initial kinetic energy. We're going to go ahead and write that in two parts. 1/2 MAVA squared plus 1/2 MBVB squared minus 1/2 for the KE final, 1/2, and then the mass is going to be MA plus MB times V sub F squared. Then when you plug in and solve for this, you will end up with a KE lost is equal to 21,381 joules, which you will probably need to reduce for significant figures, but just for your base answer, this is the amount of kinetic energy lost.